So today I'll be talking about land boundary delineation using units. This is a project that we've been working on at Mishango with the company that I work with. So a little bit about my company, then we can kick start everything. So Shango, that's a company that I'm in, and they're the ones I'm benefiting this particular thing from, finding, being able to join such a particular conference. It's on their ticket. So Shango is a social enterprise, as you can see over there, and their aim is to create data science jobs for people in Africa. And they have a mission to create high-skill data science jobs across Africa. And this is a Herculean task. So they recruit people through a fellowship. Then during the fellowship, they can give you opportunity for you to work with host companies that give the opportunity to work with real life data. So you don't get to do a lot of cosmetic works, but work with real life data to see how your model works and everything. And you also get some kind of mentorship from the data scientist, the resident data scientist at Ishango. So that is what they do, and I'm proud to be one of the people that have gone through the Ishango ecosystem, and I'm a member of them. Yeah. So this is the outline we are going to do with today. Our background, objective methodology, sample input data, the architecture of VNet, and the preliminary results on what we've done, and the impact of the project, conclusion, and some future works. So to begin with, land is a good resource, but it is also not renewable because and land is being used for other land is being needed for a lot of purposes. So in agriculture, we need land to cultivate. We need land to build homes. We need land for the industrialization purposes to build factories and the other things. So land is a very good resource that everybody would like to have one in the future for whatever purpose that he or she or whoever wants it for. And for government and for other policy makers as well, they also need land for other things. And usually, when they want to survey a land or find the boundaries of a land, they have to send a surveyor to the ground. They survey the land and find the boundaries and estimate that your land is of a certain size. But we are looking at using readily available deep learning algorithms to find the boundaries of land, so that land allocation and monitoring can be a very handy task, so that it can counter complement the already available process that is being used. That is when somebody goes there to find the boundaries of the land. So by doing so, if somebody wants to apply land for a particular purpose or anything, the person can just use our model based on the past satellite image theory and can come out and find out the boundary of the land that is because of a particular purpose or is being needed to be monitored. And so through this particular process as well, you can go to the extent of estimating the size of the land at the end of the process. So you can find that my land is this number of acres or this number of hectares based on this kind of. So that's the aim. That is what we seek to achieve. And this project, we use the UNet, a type of convolutional neural network, to learn the boundaries of land using some satellite images that we have. So there's a typical background, a typical image. So this image was taken from a certain part in the central part of our of Ghana. We call it Techima. So it is in the central part, around the central part of Ghana. So you can clearly see the boundaries. You can clearly see that some are being used for agricultural purposes, others are also bare. So this is the kind of data that we fed into our algorithm, the one that we're going to develop. We fed it into it, and was able to help us find the boundaries of the available of the satellite of the land, the parcel of land that's available here. The objective is to come up with a working model that can accurately find the boundaries of different parcels of land from these satellite images, and also to apply the model, like the working model, in areas such as agriculture. Yes, as I mentioned. So let's say they can use it for sustainable use of land for agricultural purposes, and also for land registry purposes. That is for people in government, policymakers, to be very easier for people to register their land. You can just send this kind of information. We have a satellite image of the area. We pass it through our model, then it can find the correct boundary of that particular land, and we can estimate the size of the land, and it can enter the books of the local government authority, or whichever authority that is in charge, so that they can find that this person has registered this particular land, and it helps in settling disputes, land dispute between different parties. So that's the objective that we have for this particular project. The work that we did, we had to download some satellite data. So this data, as I said, was collected over Ghana. So the data came in. These are from Sentinel-2. We use the Sentinel-2 satellite. So we combined. We were just interested in the image itself. So we just combined the band 2, band 3, and band 4. That forms the RGB image. That is a colored image. So these images were concatenated. Each of these bands were concatenated to form the RGB image. But it was also for a period of 2017. So the data was not that much. So what we did to increase the data, the number of data instances we have, was that we did augmentations to each, to them, and that's increased the number of data that we have. So we did horizontal flip, vertical. We did random crop. We did center crop. These are augmentations that from research we've seen that people have applied in the areas of image segmentation. So we applied these ones to them to increase the number of samples that we have. And the images come, each RGB image comes with a corresponding mask, which we'll see shortly. So it comes with a corresponding mask, and the boundary mark. The boundary mark that shows the boundaries of the land, the different parcels and its boundaries. So what we did was that for the mask, we normalized it to the value was between 0 and 1, and that was used as the target. And in our inference, so when the model has finished, when we finished training the model, in the inference part, what we did was that we loaded, so we actually convert all pixel values that are below a certain threshold to 0, then below and above a certain threshold to 1. And that gave us a very clear image, as in finding the ones that are, the part that is boundary and the part that is land. So that is what helped us. We use the inference, but that could help us do the classification between the land and its boundary, and that helped us to find the different parcels of land and its boundary. And we use units, the unit architecture. For the unit architecture, the encoder part, we use the readily available pre-trained model, ResNet34, and its encoder with ImageNet. That is so the encoder ResNet that we trained with the image with ImageNet. With ImageNet, and we chose a pre-trained model because it actually helps with the training. It helps you train faster than trying to load from scratch. And you realize that from the data, from what we have, we realize that it's worked well. Our model worked well using the encoder ResNet than starting from scratch. It took a very long time for us to get a very good model, a very good prediction starting from scratch. So we use ResNet34. The ResNet34 also, because of the skipping connections, right? Yeah, ResNet also uses skipping connection because of the degradation problem. Yeah, and after that, that's the model that we use to find the boundaries of the land. Let's typical example, that this is a sample of the input image. So as I said earlier, we have a satellite image and we have the full mask and have the boundary. But we're most interested in the boundary, normally the full mask. So that you can see from the boundary, we have the yellow part and we have the other color, the violet part. So that color tells you land and the yellow part tells you the boundary. And that was what we were interested in. So from here, if we have the ground truth data about the various lands, it could be labeled. And when we have the various polygon coordinates of these particular land, and we can say this land is for agriculture, this land is for industrialization, this land is for affordable home, and the other purposes that it has been earmarked for. So our purpose was just for the satellite image and the corresponding boundary mask. However, in the model, for model training, we concatenated a full mask and a boundary mask. So a model could predict both of them, a full mask and a boundary mask. But we're interested more on the boundary mask. So a little bit on the architecture of UNet. So UNet is a model that was developed basically for biomedical image segmentation by Fisher, Ronenberger, and the Brooks. They did a very good work, and the UNet is very good for image segmentation because of its nature, the U nature, where the first part of the U is the encoder, and the second part, and the other part of the other hand is the decoder, and it also uses the skipping connections, where some of the layers are skipped, and it improves the feature extraction because the input of the particular of the encoder is actually concatenated with the output of a particular layer is concatenated with the output of a lower layer of the decoder side, and this helps in the feature extraction. This helps the model to be able to extract good features out of the data that it has been given. But for the purpose of our project, we use the encoder side, we use ResNet. The decoder, we still use the unit decoder. So you can easily fix something at the encoder side and still use the other part of the unit as your decoder. And it's basically like any fully connected convolutional neural network. So it has all the blocks like any of them, the convolutional network, the convolutional layer, the max pooling, and the rest. Everything there is the same. But there is a link to it if you want to read more on it, because these are the guys that did the work on DNet. I just used part of it for my project. So at the end of preliminary results, what we've gotten so far on the project is that we have a Jakarta similarity score of 0.87 and a recall of 0.83. Then the Jakarta similarity score is a very good measure. It's a very good measure to find how similar a predicted quantity is as compared to the target, what it really is. So it finds the intersection divided by the total. So this is a very good measure in image segmentation. You check whether the pixel values were predicted well, and recall, which is a very good measure of finding how good your model was able to predict the true positives. So these are the two metrics that we use for the project. And preliminary, we see that the results are good, not excellent, but they are good, and the predictions that we are seeing out of it is also quite good based on these results that we have and the number of trainings that we've conducted so far. So what is our encouragement? I mean, we have that at the back of our mind that this particular project seeks to enhance the land acquisition process. So as I mentioned earlier, where somebody has to buy land or whatever. So someone wants to buy land for a particular purpose. Based on this kind of model, it will be a bit easier, and then the process will be a bit transparent. So you can stay in any part of the world and can use this kind of model to accurately estimate the boundaries and goes to the extent of estimating the size of your land. And it's a greater kind of transparency and trust between parties for land acquisition. It also helps in the to improve allocation of land for sustainable use. So if a land has been designated for a particular task, it's easier with this kind of model. So we have the particular lands, we have particular ID to the land. So with that, whenever you load whenever you pass the imagery data on through our model, you can tell this is the size of the land, irrespective of what has happened, whether that has been graded or plants have been planted on it or something like that. They can still estimate based on the kind of training that they have given to it. Then you can go to the extent of checking whether the land is being used for whatever purpose that it was designated for. Yeah, so that comes to the third point, monitoring land use, and it will help both government and individuals for to check proper use of land for particular purposes that it has been designated for over a period. So we can conclude in preliminary that the image net, no, sorry, the segmentation problem, which is the land boundary delineation, which is a segmentation problem, can be efficiently resolved using UNet. So UNet, because that is the main model that we used. So it is UNet with the encoder ResNet34. So in future works, we would like to try other pre-trained models like pre-trained encoder models like DenseNet. So DenseNet also uses the skipping connection, but also for to improve the feature extraction. But UNet 34 uses the skipping connections because of the degradation problem. So we want to try other pre-trained encoders to see how it works on the model and its corresponding image weight. And also, we would like to also explore using currently available data. So the data we had, I said, was not enough, so we had to augment it to increase the number of samples, the number of instances that were available. So we could find more data. So instead of picking for just a year, we could buy for a longer period and get more data, and we can take it through the augmentation. It may be as part of the training pipeline instead of it being outside the training pipeline just to increase the instances. So by so doing, using it on maybe using it on new data sets, the model can be able to learn newer boundaries between land, but maybe land allocation might have changed and the boundaries maybe over a period might have changed and the purpose of the land too might have changed. So it will be good for us to use this particular, to learn to use it on different or currently available data so that it can learn new features. And it will be good that if it learns on new features, it will be used in areas that have similar features of it in its area. Let's say if it is in Techiman areas, I mentioned, other areas that are within Techiman or that have similar landscape to Techiman, the model can do well. But to use it in another country where the architectures are different, now we need to train it with such kind of data. So we had some limitations. That is that the training takes a bit of a long time because GPUs are generally preferred for this particular work, but we had CPUs at our disposal when we were training. Later, we actually had GPUs for our project inside it. So GPUs are generally preferred for this kind of project because of the segmentation task that takes a very long time. And also with the images that were downloaded, so images usually comes as polygons. Then you pick the polygons are coordinates of the land. So each land has its own polygon. So we pick these polygons and use the Sentinel downloader to download the corresponding image of that particular polygon. Yeah. So This also takes a bit of space. It's so if you're going to do this kind of thing, we have to allocate space, some space for storing the images and the corresponding shapes as well, the corresponding polygons as well. So this is a little bit. These are some of the references, but the frame of reference that we use, the main one was from Ronberger, Fisher, and Brooks. That is the original paper on units. So that is what. So thank you very much for your attention, staying up late to listen to me, and also for the audience, for the organizers of this wonderful project that they invited me to share what I have.